Let's work out some examples of Laplace transforms involving shifts. So here is a piecewise function that is shifted. So this is 0 up until time 2, and then at time 2 it turns into sine. So to find the Laplace transform of this, we need to write this in terms of step functions because we have a nice Laplace transform rule for step functions. So, so we'll start with the initial form, the initial character of our function, which is 0. And then at time 2, something happens. Something changes at time 2. So we have to have a step function that turns on at time 2, and that's u of t minus 2. And then we have to multiply our step at time 2 by the new function at time 2. And that's the sine function. So sine of t minus 2. Okay, so this function that we want to take the Laplace transform of is u of t minus 2 times sine of t minus 2. Okay, now this is a shifted function, and it has a step that matches the shift, right? The shift in your step function has to match the shift in your in the rest of the function if you want to use the Laplace transform rule for shifts in the t world. And of course we do, so it's nice that these match. The Laplace also this shift is positive, right? 2 is greater than 0. So our Laplace transform rule says that the shift by 2 in the t world gives us an exponential e to the minus 2s in the s world. So e to the minus 2s times the Laplace transform of the unshifted function, which is sine of t. And we know what the Laplace transform of sine of t is. It's 1 over s squared plus 1. All right, so we found that Laplace transform. If the shift inside your function does not match the shift in your step function, you have to make it match somehow. You have to do some sort of algebra to make it match. And we'll look at an example like that. So how about this one? So finding the Laplace transform of t times u of t minus 1. So this has a step function, but notice that the rest of the function, besides the step function, isn't shifted by an amount that matches the step. So we can't use our Laplace transform rule on this immediately. We have to somehow make it so that we have a t minus 1 that shows up, right? Because then the shift would match the step. But of course you can't just replace t with t minus 1, because that would be different. T isn't the same as t minus 1, but t is the same as t minus 1 plus 1 times our step function u of t minus 1. So here what we're doing is we're sort of intentionally unsimplifying, because now we have a t minus 1 to work with. So then if we group the stuff in parentheses like this and then distribute that step function, what we're trying to find the Laplace transform of is t minus 1 times u of t minus 1 plus 1 times u of t minus 1. And now the shift matches the step, right? So we can use the linearity of the Laplace transform. We want the Laplace transform of t minus 1 times u of t minus 1 plus the Laplace transform of u of t minus 1. All right. And both of these, we can now use for both of these, the shift matches the steps, so we can use our Laplace transform rule for shifts in the t world. A shift in t looks like an exponential in s, so this is e to the minus s, times the Laplace transform of the unshifted function. And the unshifted version of t minus 1 is just t. Plus, over here, the Laplace transform of a shift in a step is an exponential e to the minus s times the Laplace transform of the unshifted function. What is the unshifted function here? Well, there's a hidden times 1 right there, and that's our unshifted function. So Laplace transform of 1. And we know both of these. So e to the minus s times Laplace transform of t is 1 over s squared plus e to the minus s times Laplace transform of 1 is 1 over s. All right, so we did it. Depending on if you have this situation where the shift does not match the step, how you force the shift to match the step really depends on what this function is. In general, there will be some trick like this where you intentionally unsimplify, but then there might be other algebra you have to do to sort of split things up somehow. But it really depends on what function shows up here. Okay, let's look at one more example. Let's find the inverse transform of this mess, s plus 2 times e to the minus 4s, all over s squared plus 4. So the thing that catches my eye about this one is that exponential, right? An exponential in the s world looks like a shift in the t world. So let's use that Laplace transform rule. So that exponential in the s world, in the t world, it turns into a shift. So we have to replace t with t minus 4 and multiplication by a step. So u of t minus 4. Okay, and then the rest of what we need to take the inverse Laplace transform of is everything except the exponential. So that's s plus 2 over s squared plus 4. Okay, now how you calculate the rest of this inverse Laplace transform, of course, depends on what is sitting here. And right, the denominator makes me think that we're going to end up with sines and cosines. And if we're going to end up with sines and cosines, then we need to split up the s and the s in the numerator and the constant in the numerator. So that means we'll have Laplace inverse transform of s over s squared plus 4 plus inverse transform of 2 over s squared plus 4. And then don't forget that at the end we have to shift. We have to replace t with t minus 4, and we have to multiply by a step. So u of t minus 4. Okay. Now both of these Laplace transforms, these are ones we know. The first one is cosine of t, and the second one is sine of t. And then don't forget to do our shift, replace t with t minus 4, and multiply by the step, u of t minus 4. So our final result is cosine of t minus 4 plus sine of t minus 4, all times the step function u of t minus 4. All right.